Okay, so this problem is on adding two IEEE 754 floating point number format. So I want to add two numbers in IEEE format. If you look back, for single precision, it's 32 bits each number. Now the bias is 127. That's for single precision. For double precision, it's a different value. Now, let's look at this. I have two numbers, A and B. A is this 1, and then I get 0, I get 1, 0, 0, 0, 0. So A is 32 bits. Now, the format for IEEE, as you can see, the first bit is the sign bit. If it's negative, you get 1. If it's 0, that means it's a positive number. The next 8 bits is the exponent. 1, 2, 3, 4, 5, 6, 7, 8. So the next 8 bit is the exponent. See, for this one is 1, 0, 0, 0, 0, 1, 0, 1. Now, the next 23 bits is the mantissa. So this is M. That's the mantissa, which is 23 bits. 23 plus 8 plus 1, that gives me 32 bits. How do I add these two floating point numbers in this format? Well, first A, the sign bit is 0. B also, the sign bit is 0. So that means these are two positive numbers. The exponent for A is actually 1, 0, 0, 0, 1, 0, 0. So this is A. This is the exponent for A. The exponent for B is 1, 0, 0, 0, 0, 0, 1, 1. 1, 0, 0, 0, 0. So there are five zeros and a 1. So the exponent has to be an 8-bit number. So that has to be 8 bits for the exponent. So I can include that here. That's 8 bits. Now, if I take this number here, 1000001, and I convert it to decimal, that's 132 in decimal. I have to take out the bias, 127. So that gives me 5. Same thing for B. The exponent is 100000011, so that's 131 minus the bias, which is 127. So that gives me 4. So now I have the exponent there. So what I can do, put this in scientific notation. To put this in scientific notation, I'm going to do, which is 1.1.00111, which is times 2 to the 5th. So this is how the first exponent number is. For B, it's the same thing. It's 1.010011, whatever, times 2 to the 4th. Now here's the problem. Before I can add any two numbers here, that means that the exponent have to be of the same value. So what I'll do for B, I'm going to convert this, instead of 2 to the 4th, it's going to be 2 to the 5th. So I'm going to move this 1 to the right. So this becomes now 0.101001. So this is 2 to the 5th, and this is 2 to the 5th. Now I can add them. So for A, 1.0001111 times 10 to the 5th. For B, 0.1010010 times 2 to the 5th. So if I do my straight addition in binary, 1 plus 0 is 1, 1 plus 1, 0 carry 1, 1 plus 1, 0 carry 1, 1 plus 1, 0 carry 1 unit, not 1 unit of 2. So carry 1 unit of 2, 1 plus 1, 0 carry 1 unit of 2, so I have a 1, and plus 0, so that gives me 1, 0 plus 1 is 1, 0 plus 1 is also 1. So this times 2 to the 5th. So basically, this is what I got. So I have to put this in that format, in the 754 IEEE format. Now, my exponent is 2 to the, this number times 2 to the 5th. I'm going to have to add the bias to it. So I have to take the bias 127, which is what I took from each exponent earlier, plus 5. So this gives me 132. So 132 in binary, 1 0 0 0 0 1 0 0. So if you look back, this is 2 to the first, 2 to the second. 2 to the second is 4. Third, fourth, fifth, sixth, 2 to the seventh is 128. 128 plus 4, because this is 2 to the second and this is 2 to the seventh. 128. So if I add these two numbers, I come up with 132. And that's it. So basically, I'm going to put this in a 32-bit in an IEEE 754 format as single precision, because for single precision is actually, so single precision here, it's 32 bits. So single precision is 32 bits. So the sign bit is 0. This is the exponent, 1 0, so that gives me the exponent. And then the rest, 23 bits, is the mantissa. So this is M here for the mantissa. So 1 plus 8 plus 23, that gives me 32 bits. And this is my answer after I added these two numbers. Thank you for watching this video.